In this last section, we are going to talk about synaptic receptors and the actions of receptors. So receptors are typically named for the transmitter, neurotransmitter, or neuromodulator to which they bind. So you'll have dopamine receptors or serotonin receptors. So they either produce direct or indirect actions. So the direct action is when the receptor and an ion channel make up a single functional unit. So those are those ligand-gated channels, and the neurotransmitter binding to the channel opens up the channel. That's how it acts directly on the postsynaptic cell. Usually when they act indirectly, they trigger a binding of the neurotransmitter or neuromodulator, triggers a cascade of intracellular molecules either to activate ion channels or cause other changes within the neuron. So there's a lot of detail in the book about the second messenger system, and we'll talk a little bit about it, but I don't expect you to worry too much about that. So postsynaptic receptors use two mechanisms to transduce signals. So when activated, the receptors produce fast or slow responses by ligand-gated ion channels or G protein activation of ion channels. That's the slow response. So it's sort of a reiteration of the last slide. So the ligand-gated ion channels consist of proteins that function as receptors for the neurotransmitter and as ionotropic receptors. So the gates open in response to specific chemical ligand binding to the receptor surface. The gates are closed in the resting state. So rapid and brief opening of membrane channels occurs when neurotransmitter binds to the receptor site of the membrane channel. So the ion channel receptors act like a lock and a key. The channel is the lock, and the ligand or the chemical that's going to bind to it is the key. The G protein activation of ion channels, they change the electrical excitability of neurons. So G proteins open ion channels by acting as shuttles, sort of, inside the neuron. When a neurotransmitter binds to a G protein receptor, the receptor protein changes shape, and it activates G proteins inside the neuron. And the G protein breaks free and moves to bind to a membrane ion channel, and the ion channel changes shape and opens. So it's sort of like the ligand-gated ion channel is a one-step process, and the G protein activation is a two-step process. So you can think of it that way, and that's why it's a little slower. And there are reasons why you would want it to be slower, especially if you're working on an inhibitory response. You want to alter the excitability of neurons. You want to inhibit them a little bit. So G protein second messenger system is responsible for some of the most profound and long-lasting changes in the nervous system. So G proteins activate intracellular second messages, initiating a cascade of intracellular events. So activation of genes causing the cell to manufacture different neurotransmitters or other specific cellular products, opening of membrane ion channels, or release of internal stores of calcium to regulate metabolism and other cellular processes. There's this little graphic from the book is sort of like the simple version of how G protein second messenger systems work. First, a messenger binds to a G protein coupled receptor. The G protein subunit binds to the enzyme receptor. It creates that effector enzyme. There's a second messenger which then causes effects, whatever those effects are. So really, we're going to keep it pretty simple. There's a lot of detail about how those work, but in terms of activation of genes, when we talk about neuroplasticity in Chapter 7, part of learning is either unmasking silent synapses, ones that previously hadn't been used, or changing the chemical profile of a neuron to make it do something different. That is actually the definition of neuroplasticity, is being able to change the action, the function, or the chemical profile of a neuron. So if we are using G proteins to activate genes to cause the cell to manufacture different neurotransmitters, we're changing the function, and we're able to change our nervous system. And that is a hugely powerful tool to have at our disposal. So cells regulate receptor activity in several ways. Either in response to frequent stimulation by a ligand, the cell will decrease receptor activity by receptor internalization or receptor inactivation. So if we're constantly getting this influx of neurotransmitters, the only way we can change the activity is if we get rid of the things for the neurotransmitter to bind to, if that makes sense. So there are several disorders of synaptic function that are discussed in the book. The only one that I really have in the Canvas module is myasthenia gravis, because that is the one that we frequently see in, and I don't want to say frequently, I've only ever worked with 2 people with myasthenia gravis, and it's pretty rare. I mean, you could go years and years and not see someone with myasthenia gravis. The other ones, they're mentioned in the book, and that's why I have them here. Lambert-Eaton syndrome, it's an autoimmune disorder. Myasthenia gravis is also an autoimmune disorder where the antibodies attack and destroy the receptors on muscle cells. So it decreases your response to acetylcholine. So you have plenty of acetylcholine to enact those neuromuscular junctions, but you don't have as many receptors, and so the receptor sites get filled more easily, and it decreases your muscle power. Channelopathy is a disease that involves dysfunction of ion channels, and so it can cause paralysis or slow reaction following muscle contraction, and in some cases cause epilepsy and migraines. And I don't know how it does that. It doesn't really specifically say in the book, but kind of interesting.